hope everybody enjoyed the lunch. Part two. My plan now is to talk about the observations of velocity and magnetic fields. So how we know what we are going to discuss in the next lecture. Next lecture will be about the dynamo theory. So first, in the first lecture, we discussed what are galaxies and clusters of galaxies. Now we discuss how we extract information about them from observations. And then we shall discuss how to explain what we have seen, what we have extracted. So, observations. I will first discuss the observations of a velocity field. It will be, it's basically one single method based on Doppler shifts known to everybody. And then we shall talk about observations of magnetic fields, and then we shall discuss the results of those observations. What do we know about magnetic fields in spiral galaxies, galaxy clusters, and very, very briefly, I will just, at the level of showing a couple of colorful pictures, we shall discuss accretion disks. So, the main method to measure velocities in astrophysical environments is the Doppler shift of spectral lines. So, if the source of electromagnetic waves moves at the velocity Vs with respect to the observer, then the wavelength of a spectral line will be shifted by this amount of delta lambda, which is proportional to the unshifted wavelength, and also the ratio of the velocity of the source to the speed of light. This is an example of a part of a spectrum with several lines. So this is called blue shift. If the object moves towards you, the wavelength decreases, right? Because the source sort of takes up with the waves emitted by itself. So the wavelength becomes smaller, and all the spectrum is shifted towards the blue part of the spectrum. If the source moves away from you, then it's red shift. Then the spectral lines are shifted towards red. What are the very neat, very precise method and a very universal method to measure velocities? The limitations are the following. First, only one component of the velocity, the line of sight component of velocity, is measured. And the time scales involved in the evolution of astrophysical objects about which we are talking are such that to observe the lateral motion most often is impossible, just because the objects are so far, so that the angular displacement over the human lifetime is absolutely negligible. So the parallax, the proper motions of these objects are most often, with very rare exceptions, totally unobservable. So this means that if you want to reproduce a three-dimensional velocity field, we need to make additional assumptions. For example, often these assumptions, in our case, is that we have purely rotational velocities. Then we can also use the Doppler shifts to measure random velocities. As usual in such observations, what we observe is an integral along the line of sight. If we look in a certain direction, we shall always observe the integral of all the emission produced along the line of sight. And if the different volume elements along the line of sight move at slightly different velocities, randomly spread around some mean value, then we shall see a broadening of the spectral lines. And, well, the main problem here is thermal broadening, because random motions, but definitely will not be the only reason why spectral lines will be broadened. The most important is the thermal broadening. If the gas has a temperature T, then this is the mass of the ions involved, most often protons, Boltzmann's constant, and this c is the speed of light. So this delta nu is the width of the line in terms of frequency. This is a thermal broadening. With broadening due to random motions, again, this will be, if V0 is the typical random velocity, RMS velocity, then this will be the thermal broadening. Obviously, you need this to be much larger, so the turbulent velocity should be much larger than the thermal velocity, basically. For non-thermal broadening, it's called. Broadening due to random velocities to be observable. This means that it is useful to observe spectral lines which are produced by cold components. And for example, a widespread method is to observe absorption lines. For example, if you have a turbulent region at some distance from you, and then the emission produced by this region passes through a relatively cold cloud, then this emission will be absorbed. No, still, with the absorption line, you will measure the velocity of the absorbing material. Yes. So this is the main, well, basically this is the main problem. Thermal broadening is the main problem in measuring turbulent velocities. But it's, in many cases, this problem can be overcome. And in particular, in the interstellar gas of galaxies, indeed, the turbulent velocities are more or less readily observable. This is an example of what we can do in galaxy clusters. In galaxy clusters, the situation is more complicated. If you remember from yesterday's lecture, we saw quite a number of images of galaxy clusters with these galaxies scattered around and this glow of X-ray emitting gas. These X-rays are in fact thermal X-rays. It's a thermal emission. Therefore, it has this black body spectrum and no spectral lines. Therefore, even though we know quite well the gas density in galaxy clusters, the temperature of that gas, we know very little about the gas velocities because there are no spectral lines. And the temperature of the gas is what, 100 million kelvins. So the thermal broadening is enormous. And until very recently, I thought there is no hope to get to make such measurements. But people are clever. And then I encountered this paper of Rashid Sunayev and Inaganov, who argued that thermal broadening, of course, let's look here, that thermal broadening depends on the mass of the ion involved. And for galaxy clusters, if it's a proton mass, for example, if we look at the emission of hydrogen plasma, this broadening will be much higher than hydrogen broadening, because the turbulence there is strongly subsonic, is expected to be strongly subsonic. But imagine that you observe the spectral lines of iron, which is 56 times heavier. Then thermal broadening will be root of 56 is about between 7 and 8 times smaller. And then you can really observe the spectral lines of these spectral lines of iron. They are again in the X-ray range. And this is the calculation of the expected spectral line that you can see. So this dashed line is the expected thermal broadening of the iron line. The solid is the expected shape. So what else we have here? There's the Lorentz broadening. It's this. And thermal Doppler broadening for the turbulent velocity of 190 is quite significant. So this is purely thermal. This is thermal plus Doppler shifts. Quite a significant change. So these wings here would be informative for the measurements of the turbulent velocity. Unfortunately, the X-ray telescope for which program this paper was published was never launched. It was cancelled. But still, probably with the next generation of X-ray telescopes, they will have. Right now, it's impossible to measure this line just because of the lack of resolution and sensitivity. You need just higher sensitivity and resolution of X-ray telescopes to make these measurements. It would be excellent. It would be great to measure directly turbulent velocities in galaxy clusters. we shall see slightly later, probably next week, how important it is to know what are the turbulent velocities in galaxy clusters. So, and that's it about velocities. Just Doppler shift. Doppler shifts, you can, to measure regular velocities, most often you need to make additional model assumptions. To measure turbulent velocities, your main enemy is the thermal volume. If you can mitigate it, you can have reasonably good information about turbulent velocities. Again, the main problem which remains is that you always observe an integral along the line of sight. You should be always able to decide which regions contribute to this integral and in what way. Now, magnetic fields. We know about the magnetic field of the Earth just because we have compasses, right? And it would be hard to bring compass to another galaxy. So we need the methods of remote measurements of magnetic fields. Historically, the first such method was Zeeman splitting of spectral lines. Under the influence of magnetic field, many spectral lines split into, in the simplest case, into a triplet or into a larger number of components which are differently polarized. So this was, in fact, the first observational method which allowed to detect magnetic field on the Sun in what, 1906, right?
Wait.
1908 by Hale, right? And it was done just 3 years after the discovery of Zeeman's effect. Even before there was Nobel Prize awarded for the discovery of the effect. So it was a very rapid reaction of astronomers to this new discovery. Very soon after the discovery of the Zeeman splitting, it was applied to measure the magnetic field of the Sun. But this method works perfectly well and remains the dominant method for measuring solid magnetic fields. But to make this splitting, or very often even just broadening of spectral lines, if the splitting is weak, measurable, you need quite a strong magnetic field. Such magnetic fields in galactic context only occur in very dense clouds, not in diffuse gas. There, other methods are required. And the most important of them are the Faraday rotation of polarized emission and synchrotron emission. I will discuss it in more or less fine detail in what follows. And then there is also an additional method which is based on light polarization by interstellar dust. This is an interesting mechanism. I mentioned dust, the presence of dust with interstellar gas. These dust particles, they have some magnetic properties. Some of them are of paramagnetic. And they rotate around their axis. As they rotate, they have magnetic moment, and then the external magnetic field will affect the orientation of magnetic moment of the particles. And then it aligns them, and they rotate, I think, with their minor axis parallel to magnetic field. If the minor axis is parallel to the magnetic field, this means that this particle will preferentially absorb the light whose E vector is perpendicular to magnetic field, and will transmit better light whose E vector is parallel to magnetic field. This means that if visual optical light will pass through such a cloud of oriented, rotating dust particles, it will emerge from this cloud polarized with a polarization plane parallel to magnetic field. And this phenomenon is observable. It was observed in the early 50s that the light of distant stars is polarized, and the further away is the star, the stronger is the polarization. We shall discuss again this method more. And then, as usual, whatever is your classification, there will be something which doesn't fit it. There are also other methods. So, Zeeman splitting. E here is not electric field, it's energy. The energy the energy level of an atom, electrons in the atom. If I apply magnetic field, the energy level, atomic energy level, with a quantum number m, will split, this plus minus, will split into one. Mu is just a combination of physical constants called Niels Bohr's magneton. G is a lambda factor, depends on the quantum numbers, which is just one simple function of the quantum numbers of the two atomic energy levels. So this is the split, amount of split that you can have for a given magnetic field. And it's measurable. If I substitute all the numbers, this is the amount of split in terms of frequency. 1 megahertz. This delta Gm is of order 1, and B over 1 Gauss. So for B equal to 1 microgauss, 10 minus 6, you expect splitting of about of the order of 1/3. This is the amount of splitting. The typical frequencies of radio lines which are used for these observations are of the order of gigahertz. So 10 to the minus 9th. This is small, but again, here the main problem is the thermal broadening of the lines. Because what will happen, you will have a spectral line, ideally without any broadening, right? This will be frequency, and this is the intensity of light. This is your mu naught. Now, the line will be split by Zeeman effect. But apart from this splitting, there is a thermal broadening, which can, if it is much larger than these lines, then the splitting will just make the lines slightly broader and nothing else. So in this mess, it will be very difficult to observe anything. But the advantage is that these splitted lines, they are differently polarized. One of them, I don't remember which one, the right one or the left one, has right-handed circular polarization, and the other left-handed circular polarization. So what in reality people observe are broadened spectral lines, but the rings of the lines are differently polarized. So what is detected, in fact, is a difference in polarization in the wings. And this gives you a measure of magnetic field. So these are very difficult observations. The first detection of the Zeeman effect in the external medium was done in the early 70s, the first confident detection. And it took 8,000 hours of observing time to make this detection. 8,000 hours of observing time. 8,000 hours of what? 100 hours is roughly 4 days, right? 1,000 hours is 40 days. 800 hours is more than half a year. You have to sit at a telescope without lunch, without breakfast, for more than half a year without sleeping to make one single detection. Since that time, various techniques were developed, of course. So now, these measurements, there are quite a large number of such measurements. There are even maps of magnetic fields in interstellar clouds obtained with the Zeeman method. But still, this method in the case of interstellar gas requires very high skills of astronomers. You need to be a very experienced astronomer to make such observations. And this is an example of such splits. This is the hydrogen Lyman alpha line, which is obtained with the transitions at the base level and two excited levels. If magnetic field is 0, if magnetic field differs from 0, look what a mess you have. This line splits into 4, this line splits into 2, and this splits into 2. And all these transitions, they obviously will be close to each other. From this you can also see how complicated it can be like. But fortunately, this is all based on atomic physics. This means that everything can be calculated very exactly and precisely. All these separations of all these lines are known to very high levels. But still, this is a very non-trivial and very technically complicated method to measure interstellar magnetic fields. In the Sun, it is much easier. In the sun, it's much easier. What we have here. This is the splitting of lines in the sun, right? This is the iron line. Yeah. Here, yes, look at this. This is the iron line, right? With weak magnetic field. Look what happens when magnetic field is strong in the sun, in the case of the sun. This line has been broadened, and this line has been broadened, and in this case, it even has some substructure. So this is the sort of data people analyze. So having this spectrum, you must first identify this as an iron line, and then compare it, knowing temperature, compare it with the thermal broadening, and so on and so on. So this is the sort of a data in the case of the sun, where the method is relatively simple. So this method in the case of interstellar gas works only when densities exceed 1,000 particles per cubic centimeter. More work is required if the density exceeds 10. Then you can measure magnetic fields of exceeding 1 microgauss, a few microgauss, which is close to the typical magnetic field in the diffuse gas. But still, the density required is very high. You need high density just to have strong magnetic field. You need magnetic field to be strong enough to produce a measurable signal. Then there is another method. Well, the advantages of the Zeeman method, Zeeman splitting, is that first it is said to be a direct measurement of magnetic field, because if you succeed in interpreting your line shape, something of this horrible form, in terms of Zeeman splitting, then deducing magnetic field only requires the knowledge of physical constants. So the amount of Zeeman splitting and magnetic field are related via physical constants. So no additional unknowns are involved. This is not true for other methods. All other methods do involve other, very often poorly known variables. This is why the Zeeman splitting, many people call the Zeeman splitting, the measurements with Zeeman splitting, the direct measurements of magnetic fields. And all the other methods are said to produce indirect measurements. But on the other hand, even if the value of magnetic field with other methods can be less certain, still the fact of existence of magnetic field is equally obvious from all these methods. In this sense, this distinction between direct and indirect methods, to me, doesn't seem to be very important. So, Faraday rotation. Imagine that you have magnetized plasma with free electrons and free ions, and then a secularly polarized wave propagates through this plasma. So if the direction of magnetic field is like this, obviously the electrons will prefer to move around this magnetic field. What? Anticlockwise, right? Like this. Electrons like to move along in a certain direction around this magnetic field. If they move forward along the magnetic field, they want to turn anticlockwise. Now there comes electromagnetic wave, secularly polarized, whose electric vector also rotates. If this rotation agrees with the direction of magnetic field, so it pushes electrons in the same direction where they want to go, obviously the electrons will be happy to help this wave to propagate. And this wave will propagate at higher speed, higher phase velocity. If otherwise, the polarization is wrong in this sense, and this electric field of incident wave tries to prevent electrons from rotating as they want to do around the magnetic field, this wave will suffer for its stubbornness. And its propagation velocity will be lowered. So, if you have a magnetized plasma This is what is called birefringence, magnetic birefringence. Did I have this clever word here? No. It's called magnetic birefringence. Oh, yes, here. So you can describe it in terms of the different phase velocities of the differently polarized waves. Or you can describe it in different refraction indices of different of waves with different polarization in magnetized plasma. Now, imagine now that what enters the magnetized plasma is a linearly polarized wave. So the electric vector oscillates in a certain plane. I can always decompose uniquely any linearly polarized wave into superposition of two secularly polarized waves with different secular polarizations. So here, this is my magnetized plasma, and my linearly polarized emission will enter with this position of polarization plane. I will decompose it in two secular polarizations, and then over this distance, one polarization, secular polarization, will propagate faster, and therefore the electric vector will rotate by a large angle, say 90 degrees. The other wave with opposite polarization will propagate slower, and therefore, or the other way around, the phase shift will be smaller. Anyway, there will be phase shift between two waves. So if here I decompose this into linearly polarized wave, into secular polarizations with phase difference, say this much, here the phase difference will change. Now we will add together, back together, these two polarized waves, but because the phase difference is different, the polarization plane will change. This means that a linearly polarized wave, while propagating through magnetized medium, will have its plane of polarization rotated. And this is exactly what is called Faraday rotation. So linearly polarized wave turns its polarization plane as it propagates through the medium. So we propagate it through polarized plasma. If the incident wave has, for example, polarization such that E vector oscillates in the vertical plane, on the exit from this region, there will be some difference in the angles, in the polarization angle from the original polarization. And remarkably, this amount of Faraday rotation is proportional to the wavelength squared. Very simple and strong dependence. Square is a very strong power. It's more or less easy to detect quadratic dependence. It's a strong dependence. That factor of proportionality, which can now it depends on magnetic field. Here is the expression. Again, it's line of sight. It's an integral effect. And this Rm is given physical constants times the integral of amount of free thermal electrons times magnetic field. Oh, it must be ds here, of course. ds. It's the line element along the line of sight. So this dot product means that only magnetic field along the line of sight contributes to this integral. Right here with ds. So, if only we could measure this coefficient for proportionality in this dependence of polarization angle on lambda squared, we would be able to know what is the weighted value of magnetic field along the line of sight. And this Rm can easily be, more or less easily obtained from multi-frequency observations. Imagine this psi naught. This psi naught, we should discuss where from it comes. It is, suppose it's unknown. Psi naught is unknown. You want to calculate Rm from this. Make measurements at two wavelengths. Psi 1 at wavelength lambda 1. Psi 2 at wavelength lambda 2. Take the difference. Psi naught will cancel. And you will get this Rm. Or if you wish, Rm is equal to d psi derivative by d lambda squared, or finite differences. What is remarkable here is that this Rm depends on magnetic field itself. If I replace B by minus B, Rm will be replaced by minus Rm. So this Rm has a sign. And the sign of Rn will tell me whether the magnetic field is directed towards me or away from me. And it's a very useful thing. But disadvantage, as usual, is that we observe a whole integral along the line of sight. So the problem is, knowing the integral, find the integral. Impossible, right? Impossible. So, but this is life. You have to live with what you have, right? We shall discuss how. Obviously, then what you should do, use various model assumptions. If you are lucky, these model assumptions will be straightforward and uncontestable, obvious. If you are not, you will be in trouble. We shall see examples of both successful analysis and cases where people are really in trouble. So, in addition, it's an integral, right? It's an integral. It's the mean value. Imagine that, let's put n equal to 1. Then this is just the average magnetic field. This integral is just the average magnetic field along the line of sight. Fantastic. It's almost exactly the same thing about which theoreticians talk. About, well, it's important to remember what Karl Heinz said about the relation between the various averages. That ensemble average and volume average, or time average, volume average in this case, can be quite different things. But in real life, I think most often people, well, there are even worse problems to worry about. Most often people don't worry about that and just identify the magnetic fields obtained, well, with the residual methods from such observations with those magnetic fields which follow from solving the equations. But it's a general problem, it's not only here. For example, what Chris was telling about us about magnetic field of the Earth. It's a similar thing. What is solved are mean field equations very often. Or anyway, some averaging is involved. And very often, when you solve equations, you use a different type of average than the average which comes from observations. So it's a general problem. This is an example of what you can observe. This is the galaxy M51 familiar to us. And these are the observations made by Andrew Fletcher, who is in Newcastle now, and Rainer Beck from Bonn. And these are, I think, most, if not all people will agree, that these are the best observations of galactic magnetic fields to date. The highest available resolution, the highest available sensitivity, the most careful observations. These are two radio maps. So the background images, the optical images of this familiar galaxy M51. This is the companion galaxy. The background images are identical. And contours show the total intensity of the synchrotron emission. Synchrotron emission, we shall discuss it in a moment. It's the emission produced by relativistic electrons, cosmic rays, in magnetic field. It's polarized, so we know the orientation of magnetic field. So these dashes show the orientation of magnetic field at 3 centimeters wavelength and 6 centimeters wavelength, at two different wavelengths. If you look here, you can calculate now this integral by taking the difference in two angles and divide by difference of the squares of wavelengths. Let's see if we can see any difference. So I expect that these polarization angles will be slightly different in the two galaxies, their orientation. So look here, what we have, oh gosh, almost the same, right? What about this one? Also very similar. The differences in polarization angles are apparently quite small. Of course, we need to find the same position. For example, here, there is a strong spot here. This is how the polarization frame is oriented, right? Oh yes, there is some difference, right? Small, but noticeable, even with the naked eye. Here, wavelength is very small, 3 or 6 centimeters. And we have here the wavelength squared. So it is profitable to observe at longer wavelengths. The longer, the better. And the very informative, more informative maps come from observations not at 3 centimeters, but at 20 centimeters, where lambda squared will be, what, 36 times larger. Then, if lambda squared is 36 times larger, then correspondingly the amount of radio rotation will be larger. But even here, we see that it's not hopeless, right? It's not entirely hopeless. There are some dashes which obviously are slightly different in these two maps. So the next image will show you the map of RM obtained from these two maps. So you take it pixel by pixel, you take the difference of these two angles, you divide by the difference of lambda squared, and you get what I will show you in the next map. But before we look at it, first let's confirm to ourselves what we see here, a very nice, beautiful, well-ordered pattern, right? Very nice and beautiful, well-ordered pattern, which is roughly the same in both maps, which clearly tells us there is a very large scale and very strong order in magnetic field. So, what about RM? What about the difference? So this is, color shows the map of RM, of the difference between size divided by difference of lambda squared, in the units of radians per square meter. Red means plus 100, dark blue means minus 100. Gosh, it's complete mess. It's complete mess. And it's clear why. We have to take the difference of two observables. Of course, all the errors immediately are boosted. It's the same as differentiating an observed noisy quantity. Differentiation leads to strong enhancement of noise. And here, the noise is especially high because observations have very high resolution. This is the size of the telescope beam used in these observations. It's already comparable to the turbulent scale. So even though with naked eye you don't see these small differences in polarization angles, when you study calculations, these differences are significant, they are noticeable, and I remember when Reinenbeck and Andrew, they first obtained this map, they were strongly disappointed. Because all the observations, which much poorer resolution of this stuff, so factor of several poorer resolution, were by far smoother and well ordered. But then, why? You increase resolution, the noise is higher, you are now close to resolving turbulent scales, of course it must be noise. So, to me it was very good news, because here with this map, you can now not only study the underlying large-scale pattern, which we shall discuss, you can also fruitfully study the fluctuations, the turbulent magnetic fields. So, all these spots, right, they are not just observational useless noise, of which you can get rid. They carry information about real fluctuations in the real interstellar video of these kinds. So, to me, this spotty and horrible map looks like a great Christmas present. It contains lots of information, both about large-scale fields and about their fluctuations. And these are indeed the best data available about any spiral galaxy in radio range. These are really excellent data. It took for several years for Andrew Fletcher and Reinenbeck to obtain this data, to reduce them, and then to convert them into such maps which can now be analyzed and interpreted. It's an achievement. To my mind, to my opinion, it's a great achievement, this data. And we shall extract lots of interesting results from this data. Yes?
Could you show the corresponding mean field picture?
Yes, yes, I will. Do you want to see it now? Let's see it now. I will just jump forward. Yes, this is a result of fitting to that picture. But now it's 4 wavelengths. I only showed you 2 wavelengths, 3 and 6 centimeters. We also have the data at 18 and 20 centimeters. So another pair of wavelengths, but now removed quite far from 3 and 6. And then we fit it to those distributions of polarization angles directly, not RF, but the almost original information. We fitted the, we introduced rings within the galaxy. And within each ring, we fitted Fourier, some superposition of Fourier modes in azimuth. and we included as many Fourier modes as required to achieve, to satisfy the chi-square test. So these are statistically good fits. It's not just naked eye fits. These are statistically good fits which satisfy the chi-square criteria. This, and since we have two pairs of wavelengths, for reasons I will not be mentioning now, but I will just make a statement. Wavelengths of different waves of different wavelengths originate from different depths in the galaxy. The 3 centimeters, the galaxy is also transparent to 3 and 6 centimeters regular emission. But we had another pair of wavelengths at 18 and 20. At those wavelengths, polarized emission doesn't penetrate far, and we only see the upper layers at 18 and 20 centimeters. This means that by comparing this data, we can decide what are the field structures in different regions along the line of sight. So we can get some information about the integrand from the integrals in this case, just because our data. So we were able to determine the field configuration, large scale field configuration, average over sort of this sort of a scale, separately in the disk and in the halo. And amazingly, look at this. In the disk, it is mainly axisymmetric field, strongly modulated by the spiral pattern. There are two spiral arms. So the mode content of this field is m equal to 0 and m equal to 2 modes. So it's an axisymmetric field modulated by spiral arms. Look how it's nicely aligned with the arms. This is the field in the halo. Look at this, it's oppositely directed. And moreover, here it is dominated by m equal to 1. This I don't know. I don't know how it is. Simply don't know. God knows what. Why it is m equal to 1. But remarkably, the field in the disk and halo have entirely different configurations. And this m equal to 1, it's sort of a headache now. I don't know how to.
So do you know which side of the halo?
Near side.
Because of the 20 centimeter.
Yeah, because we are sitting here, we see. Unfortunately, we don't know what happens on the other side of the halo. We cannot see through. And this is sort of a. These two results is just skimming the cream from the data. If you dig deeper, there will be fantastic things with this data. It's really very useful data. We also use this data to discuss the compression of magnetic field in the shock films, in the arms. Also very useful.
But yes. You have a Z component also in the halo?
No. The Z component is included into the field. The field includes all 3 components of magnetic field. Whatever number of M modes you need, plus BR defined BZ, all 3. And all these both fits don't require BZ. BZ is equal to 0 within errors. This is out of the fit, it's not because we neglect it. Not because we neglect it.
So this was done by using the polarization ink.
Yes.
If you instead would use the RM and create a mean field from that, and
This
compare
is
to
done
that
using
picture,
both.
Results will be similar but poorer.
poorer,
Yeah,
Maybe
because
not.
RM is obtained from the same data we were using,
that's
but with an intermediate step. All intermediate, with data interpretation, all intermediate steps, they only make things worse. Unless you just, for example, improve signal to noise ratio or anything like that.
But
So before us, people were using RM to fit. And it was always, there is more ambiguity when you take the difference. We only look at differences. So we fit directly polarization angles. Of course, RM is built into the process. Because the interpretation method does assume that the difference in between polarization angles is due to RM, to some earlier rotation. Plus, now we can include also such things, which are impossible to include if you directly look at RM. We introduce the depth to which we see at different wavelengths. And it can be different, for example, at 18 and 20, if needed. So what? I must go back, right? Because it can be difficult to stop me if I start talking about these things.
Which is okay.
Is it?
Oh, you're running on battery, right?
Yes, I'm running on battery. You mean here?
No, I mean on your...
Yeah.
My power by any chance?
I have power, yes, but it's okay. Oh, wait a minute, it comes to the end indeed. Yeah, I should. Sorry, I will switch on my. I will switch on my.
No, wait. You continue.
Oh,
I'll give you mine.
Hmm?
You continue. I give you mine.
Okay, thank you. So this is the sort of the data people use when making analysis of this sort. Before we continue, I want to present a small calculation which we shall need later when discussing magnetic fields in the clusters. So with random magnetic fields, what is important, for example, here, it's clear that not only the mean value of Rn around this image is important, but also fluctuations. So we need to learn how to calculate the errors in Rn, physical errors. So here is a small calculation to calculate the autocorrelation function of Rn. So suppose this Rn, this is our variable, and suppose you have magnetic field with a given autocorrelation tensor, Mij, is similar to what Karl-Heinz was using. From the fact that divergence of V is equal to 0, these longitudinally transverse correlation functions are related to each other. So suppose that you have purely random magnetic field with given autocorrelation function. Calculate the autocorrelation function of Rn. This is the problem. So it's a standard calculation. I need to calculate the average of Rn at x1, or position x1, times Rn at position x2. Just by definition, we shall direct our, we shall introduce reference frames such that this direction to the observer is the z direction. So x, y are in the plane of the sky, and z is directed towards us or away from us to have a right-handed coordinate system. So you quickly transform this to this expression. And assuming, for example, that the autocorrelation function is a Gaussian, just for simplicity, you get the autocorrelation function of Rn. And for example, let's look this autocorrelation function that you get. Let's look at the standard deviation, the value of autocorrelation function of Rn for R equal to 0. This is the expression for the standard deviation in Rn. K is a physical constant, and E is the RMS value of electron density. B is RMS value of magnetic field. Look at this square root. LB is the scale of magnetic field, and L is the line of sight. This is the distance over which you integrate. It's this L. This means that the bigger is the region, the stronger will be the scatter in Rm. It can be easily understood because, again, Rm is equal to psi1 minus psi2 divided by the difference in lambda squared. So as emission propagates, radio emission propagates through a random magnetic field, polarization angle will be rotated by this field, but the field is random. So this rotation will be random. And the polarization angle will experience random walk. So the difference, psi1 minus psi2, will experience random walk. It will increase as a root of distance. The random walk law. Here we are, root of distance. But important message to learn from here is that the errors increase, the noise. But this noise can be useful. If you can detect this noise, this means you can calculate, for example, if LB is known, where most often NE and B are known from other sources. This means that if you can measure this sigma rem, you can, for example, calculate LB. And this is what we did for M51 from this data. And then first it looked like cheating. The data I showed you for M51 are of very high resolution. So what we did was the following. Imagine that your resolution is like that. You take your map, some part of the map which is more or less homogeneous, and you will see this patchy part in RM, all this mess, which in fact is produced exactly by these fluctuations. Exactly by these fluctuations. And then you take observations with this resolution and calculate sigma RM with this resolution. Sigma RM theta, depending on resolution, or resolution D. This will be equal to sigma RM, this resolution for perfect, these are the standard deviation for perfect resolution, divided by what? Square root of turbulent cells within your telescope beam. Right? So sigma RM divided by the size of your beam times the turbulent scale. Because it's an area, right? The number of turbulent cells within your telescope beam will be equal to the ratio d squared, this is d, divided by the turbulent scale squared, the ratio of two areas. Fine. This means that you have sigma RM of d. It depends like 1 over d. And sigma RM you know. It also depends on LB. You can calculate LB. By now you take the same map, smooth it to a higher resolution. This means you have a different value of d, d1. Do the same and plot your standard deviation as a function of d. If indeed it will be close to hyperbola, this means that this works. And from the fitting this hyperbola, you will calculate LB, the least known quantity. Amazingly it works. So here it looks like cheating. You take a map with the highest resolution, then smooth it, and smooth it again, and smooth it again, and smooth it again, calculate the standard deviation of the signal within this smooth beam, and you get some useful information. So this noise is a useful thing. The result was 50 parsecs. And if you remember from yesterday's lecture, we estimated the turbulent scale from the supernova explosions of something of the order of 100 parsecs. It can be better. The agreement can be better. So, and this, to my knowledge, is the only available estimate of the turbulent scale in an external galaxy. Not in the Milky Way, but in an external galaxy. Obtained almost for free. You don't need, they just observe once and then just average. So this is a useful formula, and we shall use it again in application to clusters of galaxies.
Because Boston, even for the Hydra thing, they have all these sophisticated inversion things, but they don't have a mean field. You probably have to
You don't need mean field here. I'm talking about only sigma m. In fact, I remove the trends before doing this, and of course you remove the regular trends. You only need fluctuations.
So I don't know whether it's worth going through that algorithm.
But you know, but we have so rich and so abundant data, we don't have time to process, to interpret our own data. So interpreting somebody else's data
Not that data.
for free, I
Not
won't do
that data, but using that algorithm to interpret your data.
But why? This is better. This is simple and straightforward.
They get other information. They get the
Mass spectrum or something.
no, the information about the force or a correlation function of the magnetic field.
Correlation function.
Both are the correlation.
No,
That's
the-
just theoretical.
It's the Lorentz force. I mean, the stretching factor of Shekoshihin's.
Yeah, but that is just calculated by theory. I mean, they haven't estimated from data.
But they do it from observations.
Okay.
But
Or at least
what?
they have to
I don't know.
look at
I never looked carefully into their method and results, but I'm strongly suspicious. I'm not aware, even in laboratory. Have you ever heard about reliable measurements of the autocorrelation function of turbulent flow in laboratory, where everything is under control? I never heard. People never do it. Because even in a laboratory, where you can put your probes everywhere you want, and measure for as long as you want. Even then, statistics is too poor. And now when somebody comes to me and says that he measured the fourth order correlation function in Hydra, or whatever, it makes me so skeptical.
I see, yeah.
Right? So I would prefer to pursue simple methods like this.
That's good.
Square root of n, hyperbola, fitting a hyperbola. This is okay with me. But fourth order correlation function from observation.
No, that is a different thing. But the first thing was just a power spectrum.
It's a second order correlation function. And the second order correlation function is not measurable in laboratory too. What we are talking about, Chandra? Of course, people discuss spectra also in laboratory, but do they publish the errors? Are the errors reliably estimated? Because most such analyses, they get correlation function, beautiful curve, without errors. If I see observational data without errors, I'm not inclined discussing them. It's a waste of time. But okay, I'm talking about something without people who did that. It's something different. So, what are the results of this analysis? So, one of the main sources of information magnetic field using this method is the following. We see it somewhere here within the galaxy. But then,
sorry, one more thing to
yes,
you had from the canals an estimate of this same scale.
no, there you have the estimate of the Taylor microscale.
Right now you have
No, the
the
integral
outer
scale.
scale.
This is the outer scale, yes. This is the outer scale. Integral scale. We are sitting somewhere here within the galaxy. And there are quite a large number of sources of polarized radio emission in the universe, mainly quasars and radio galaxies. So we see such a radio source. It emits some polarized emission with some electric vector, and the magnetic field in the intergalactic space is, well, further rotation, not magnetic field, further rotation in the intergalactic space is rather weak, mainly because the electron density is low here, plasma density. So therefore, while propagating through an intergalactic medium, the rotation is relatively small, but it's unimportant. I don't care much about that. But as soon as the emission enters the region of relatively strong magnetic field and dense plasma in the Milky Way, then the polarization angles start rotating, and this I can detect. By the way, this background image is an S0 galaxy. Famous galaxy S0. You see how it looks, right? Strong bulge, and indeed there are no spiral horizons. So the typical results are the following. For the electron density of 0.03 per cubic centimeter, this is known from independent data, for magnetic field of 5 microgauss, for path length of the order of 1 kiloparsec, sort of typical values. You will get Rm, which is multiplied all of them, of 100 radians per square meter. This means that 21 centimeter polarization angle will turn by 200 degrees. You know, like almost 100 degrees, half the way. At 3 centimeters, it will be 50 times smaller, 4 degrees. You see how important is the value? Because the amount of radio radiation depends on lambda squared. If at 20 centimeters it's 200 degrees, at 3 centimeters it will be only 4 degrees. In optics, it's totally another. This is why all these observations are always done in radial range. When lambda ranges from sort of 3 centimeters, probably the smallest wavelength, up to meter, probably, right? Now there are brave people who make measurements at meter wavelengths. Very successful. Now, where from comes this polarized emission? The main mechanism is synchrotron emission. If all spiral galaxies, all active galaxies, are filled with cosmic rays, relativistic particles, whose origin, as the origin of anything else in the universe, isn't quite clear. How exactly they are accelerated. Most probably they are accelerated by the cell supernovae and by shock waves that they just emitted. And they are accelerated to quite high energies. The electrons we shall be talking about have the energy of 1 GeV, giga electron, a few electron volts. But there are cosmic ray particles with energies up to 10 to the 90th, 10 to the 20th electron volts per particle. Huge energies, huge energies. So, if such a particle enters magnetic field, it starts gyrating around the magnetic field. Since it has acceleration, it emits radio waves. And the emission will be polarized. It will be, and when you average over trajectories of many particles, the total emission will have the polarization plane orthogonal to the magnetic field. So you have a magnetic field somewhere far away from you in a distant galaxy. And if there are electrons, relativistic electrons, and there are abundant, there are in all galaxies, in all radio galaxies, in all active objects, then you will observe polarized emission in the radio range, synchronous emission, with a polarization plane perpendicular to the magnetic field in the plane of the sky. So if magnetic field is like that, then the part of magnetic field which is along the line of sight is unimportant. We can forget about it. We take magnetic field only because it's because of the averaging. And because the emission is just because of geometry. And then what is important is magnetic field in the plane of the sky, and polarization plane will be orthogonal to that component of magnetic field. Here, the amount of energy emitted per second, per cubic centimeter, per unit frequency range is given here. AFS is some function of the spectrum of electrons of order 1. Electron mass, electron charge, electron mass, c squared, magnetic field appears here. This Q, what is this Q? I don't remember now. Shouldn't be here something. Ah, yes, it's the total number of electrons, yes, this Q, total number of electrons. And again, magnetic field appears here, and frequency appears here. This S is the index, spectral index of the electrons. This synchronous emission, in most cases, is observed to have a power law spectrum. From this formula, you immediately see that if this nu is a power law, this means that electrons themselves, which produce this emission, have also power law distribution energies. Yes.
Everywhere we look, we see cosmic wave vector, CMB.
Yes. The spectrum looks like this. If I plot now the whole spectrum, this is nu, and this is intensity. Then what happens? I will have synchrotron contribution will be like that. It's this, right? Nu to the power minus s. And CMB behaves like this, goes here. So there's a broad range where synchrotron dominates over CMB. They intersect at a few gigahertz, 1 or 2 gigahertz. So above 1 gigahertz, CMB dominates, and then this stuff is a headache for them. People who observe CMB, they want to subtract synchrotron to get useful signal. But at smaller frequencies, it's okay. The synchrotron dominates. Then at still smaller frequencies, there will be free emission, thermal emission, which has a very flat spectrum. But again, there will be a window where synchrotron dominates. And this window is roughly between 3 centimeters, well, let's put 1 centimeters, to sort of couple of meters, I think, in terms of the wavelength. So this is the working range of radio astronomy, where synchrotron emission dominates. So it's a problem, CMB, but solvable.
There's the other way around. For cosmology, for example, can you probe the magnetic field signature of the CMB?
Oh yes. I think, for example, honestly, don't tell it anybody, right? But honestly, I think with this Planck mission, They will, especially with observation of polarization of CMB. They learn very little about CMB. That we shall learn a lot about magnetic fields. This is my feeling. That all these difficulties, because what they are doing to have a useful signal for CMB in polarization, they need to clean away the contribution of the Milky Way, which is difficult. So then, better to study the dirty water which you throw away with a baby, together with a baby.
High
This dirty
frequency,
water is a useful thing to study.
not at high frequency, there's not that problem.
Still there's a problem. They all they keep, well, still you have this tail, right? You have this tail.
No,
This is
it does
in
dominate.
polarized emission, it's even
Yeah,
stronger.
it's even stronger, and also in fluctuations, it's even stronger. Okay. But since Planck has, the important thing is the CMB is independent, the temperature is independent of heat. You have a thermal spectrum.
Oh, yeah.
So they are able to separate.
So this is the square, right? Relay Jeans part. The square. Well, of course it was logarithmic. I was doing logarithmic. It's log nu. So power law becomes straight line.
So I think at high frequency you can get the fluctuation even in the polarization. Already
You
there
can,
is.
you can. Of course you can. But how to interpret them? But anyway, let's not
No, no, already
argue
there is-
about the future of the Planck machine. Whatever it is, it is useful.
But even in WMAP, they have the information about the, what is called the E-type polarization from the CMBs.
Yeah. But still, the results are quite useful for magnetic fields of the
Yes.
Milky Way.
The low frequency things are useful for the field.
So this is what happens. And this emission is readily observable from a majority of galactic typologies. It's a fantastic source of information. So automatically, because the magnetic field is involved, this emission is polarized, and degree of polarization is related to this spectral index of the electron energies. It's of the order of 70% in ideal case. There are mechanisms which, propagation mechanisms, which do reduce this degree of polarization while emission propagates. So this ideal maximum degree of polarization of 70% is very rarely observed. Typical degrees of polarization observed in spiral galaxies is of low 10%, 5%. But still, since the signal is strong, it is a strong observable signal. So it's a fantastic tool. Human beings are lucky to have something at their disposal. So polarized emission whose polarization plane is orthogonal to magnetic field orientation in the plane of the sky. And just great for you to observe. And so the total intensity of synchrotron emission will depend, and again it will be of course integral along the line of sight. It will depend on the number of cosmic ray electrons per unit volume times magnetic field at this point, all integrated. If magnetic field is partially ordered, so it consists of the large-scale field and fluctuations, as Karl-Heinz described. Then, so I decompose magnetic field into the large-scale field and small-scale field, and then the large-scale field will produce polarized signal, and small-scale field will produce unpolarized signal. Just because if I have a beam, telescope beam, like this, and there is a large-scale magnetic field which is uniformly directed across the beam, of course I will observe polarized emission with this plane of polarization. If otherwise, within my beam, there are many turbulent cells with different orientations of the field. Obviously, here the polarization will be cancelled completely. And this sort of medium will emit unpolarized emission. Synchrotron, it will be the power low spectrum, it will be synchrotron emission, but it will be unpolarized. So, partially polarized magnetic field produces partially polarized synchrotron emission. This means that from the amount of polarization, in ideal case, you can determine the ratio of B small to B large. Fantastic. Fantastic. Fantastic data. What happened? Bill Gates always does something unpleasant. Just always. this intensity of singleton emission is sensitive to magnetic field in the plane of the sky, in the plane of this black hole. But we have a higher dilatation measure, where it was here, Rm. This is sensitive to magnetic field along the line of sight. So we have two complementary observables. One is sensitive to magnetic field in the plane of the sky, the other along the line of sight. So we have observables which are sensitive to all three components of magnetic field. The only difficulty here is if Rm, let's go back a little bit. If Rm is a good variable, and it is sensitive to the sign of magnetic field, right, Bz itself. Intensity of polarized emission is a worse thing. It is sensitive to B squared. This is why then B squared means the information about the direction is lost. This is why on this map there are no errors. There are no errors here. These are polarization planes, and we don't know from this data alone whether the magnetic field is directed this way or that way. We only observe B squared in the plane of the sky. But with the help of Fry dilatation measure, which is sensitive to BZ, we can put the arrows where they belong. And that map I showed you had arrows. We can determine them with some effort. So this is the sort of observations we have.
But the magnetic field from rotation measure might not have anything to do with the one that produces the emission.
So, say it again, sorry?
The magnetic field that you infer from rotation measure might have nothing to do with the one that produces polarization at the emission location.
In principle, yes. In principle, yes. But it would be, but the experience shows that, for example, let's think why. Rm, let's think what are the possible difficulties here. Rm is the integral from 0 to L of Ne, these are thermal electrons, right? Times B along the line of sight, dx. Simple intensity is equal to the integral from 0 to L and cosmic rays, right? It's a different electrons. Times B perpendicular squared times dx. So, in what case these two variables can be sort of unrelated? If, for example, thermal electrons and cosmic ray electrons are completely disjoint, so there is a region of relativistic plasma without thermal plasma, and then next to it, along the line of sight, there is a region of thermal plasma without relativistic plasma. Such cases happen rarely, at least in normal galaxies. In active galaxies, such things do happen, or in pulsars, for example. In pulsars, indeed, we have Ne equal to 0, but cosmic ray, relativistic particles can be about, because they can be relativistic electron positron plasma. Or other case, where, for example, in some region, in one region, magnetic field is perfectly directed towards you. In the other region, it's directly across the line of sight. Again, this is improbable. This is relatively improbable. And especially in the case when you observe external galaxies, which are relatively small regions in the sky. There, for example, M51, I think on the sky, its size on the sky is sort of maybe that big, angular size of that galaxy. You can vaguely see it with naked eye. This means that there is a galaxy like this, we observe it from a distance, and we see some signal. And there is nothing around to produce this signal. The Milky Way, of course, will produce such a signal. But the probability that there is some small-scale feature of this size and so strong and isolated exactly here is low. And moreover, you can check in different tracers, for example, observe thermal gas without tracers, if indeed there is any obstacle in exactly that direction. So, in theory, it's true. But in practice, I don't think it's a serious problem. Apart from active regions, active galaxies, where God knows what can happen, where indeed there can be pure relativistic plasma in one place, purely thermal in the other place.
One more comment, because when I was once giving a talk, Dipanjanas made the same remark, and one remark which I was trying to tell him is that the cosmic rays in our galactic context are being produced from supernova remnants. So they are actually being produced from a small component of the thermal particles themselves, to that extent.
Oh, yes. You accelerate thermal particles to
And the tail to relativistic this thing. So it is quite possible for them to be mixed in much easier in our galactic context than in the AGN where it's just some blob or something.
large scale regions
Yeah,
filled with.
Yeah.
And you know what? I can also put it that way. As elsewhere in any other science, there are lots of assumptions which can be justified. And then the best way to do is to proceed carefully. And if you will see that something goes wrong, make one step back and reconsider your assumptions. People try to be reasonably careful here. And these assumptions that these two variables probe the same medium, when such assumption is reasonable to do, generally it works. There are more dramatic assumptions which still surprisingly seem to work. For example, if I go back one slide, I have here these n-cosmic rays. To calculate, given that I have measured I, this intensity of central emission, I want to calculate B. I need to know the number of cosmic rays. How? The only observable related to cosmic rays is either this synchrotron emission, or recently they also produce diffuse gamma ray emission. So to use this formula to calculate magnetic field, I need to know something about cosmic rays. And until very recently, nothing was known independently. Now, cosmic gamma ray data are gathering, but very often they add confusion rather than information, as it often happens. So, the very popular assumption is the following: assume energy competition. Assume that number density of cosmic rays is just directly proportional to B squared. They have equal energy density. This assumption has no physical justification. It has hand-waving justifications. I can now start handing waves, and if I really push you hard, I will half convince you that it may make sense. But I will feel guilty because I will lose because there is no justification for it. But having nothing better to do, people use this assumption. And this is a huge hole, not hole, but this is a huge assumption. It can distort the data. We are now working on this, and maybe this assumption can be improved. Maybe you can improve it to some extent, this stuff. But it's not easy. It's not easy. So this, I think, this assumption is more dangerous than this, with the difference in the regions. So, as in any other thing, as in any family, there is enough internal dirt to make the external dirt just nothing. Okay, fine. So, knowing the degree of polarization, ideally, we can estimate the ratio of the large-scale field to small-scale field. And by the way, the result is that in the Milky Way, D squared over large-scale B squared is of the order of 3. So the magnetic field is dominated by the fluctuating component. This is a typical data. This is the map of the Milky Way. What is shown is the total intensity of synchrotron emission at 73 centimeters. This is a classical data. It's one of the best data of this sort. Relatively old, from 1978, I think. But still, in many respects, unsurpassed quality. So, this is a galactic plane, the Milky Way as we see it across the sky. This is the galactic plane. This is the galactic center. You see the absolute maximum of intensity from the galactic center. This is the local arm, spiral arm. Here, we sit in the spiral arm, right? If this is the galaxy, the Milky Way, there are the spiral arms here, and here, and here. We are sitting somewhere here. This is the sun. And in this direction, we look exactly along the line, along the local spiral arm. This is the opposite direction. So, two directions where we look along the spiral arm, therefore the intensity is higher. This is the next outer spiral arm, Perseus spiral arm. This is a famous feature called the North Polar Spur. North Polar Spur. In fact, even though it's so big on the sky, it is a very local bubble produced by supernova. This is a supernova shell, which is very close to us. This is why it has so large angular diameter. There are many other shells which are less prominent, but still, with careful inspection, you can see them. For example, there are similar shells here and here, big shells produced by supernovae. What else? This is the anti-center direction. This is the anti-center direction. When we look directly back away from the galactic center, these are the galactic poles, North Pole and South Pole. Ah, here is the map, right? So what else we have interesting here? This is the Sagittarius arm. Here, this is the next inner arm towards the galactic center. This is the local arm. This is the Perseus arm. This is the tangent to the Carina arm on the other side again. This is another spiral arm somewhere here, and so on and so on. And this is a result of deconvolution of this map. These clever people, Boerman, Kahnbach, and from Berlin, and Elie Beckhusen from Bonn, they took this data and they deconvolved them in 3 dimensions. And this is the result what seen face on. Here, you see, the paper of 1985. This image was printed with a matrix dot printer. It consists of X's, Y's, and O's. So, this is the sun here. And this is how the spiral pattern looks according to this deconvolution. So we are sitting roughly between the arms. We are the local Orion arms, in fact, just a small branch of a spiral arm. This is the Perseus arm. This is the Sagittarius arm, which continues into Carina. When we look here, we see that bright maximum in the center. Right? And this is the view from the same paper for edge on. This is the edge on image of our galaxy, deconvolved. And this is the face on. Again, familiar picture. Again, you see this large scale order, which in fact hides behind it lots of disorder, lots of useful disorder. This is another example of recent good observations, M33, observed in Effelsberg in VLA by Fatimata Batabai in Rheinberg. Again, this is the familiar galaxy M33. Remember, the one with open spiral arms and very clumpy spiral arms. This is magnetic field. You see, it's very open spirals, very open spiral pattern. But what is amazing is that even though this galaxy is very patchy, we need to make an effort to see the spiral arms, right? Still, the magnetic field remains very highly ordered. Magnetic field is much better ordered than the optically visible matter. And this happens again and again in many galaxies. Magnetic field somehow leads its own life. It is better ordered than at least optical images of the galaxies. This is an example of the galaxy M81, this galaxy visible edge on. And here we can see magnetic fields at larger heights above the disk. You can see that it's roughly horizontal. There are some deviations. More sensitive observations show that these magnetic lines further, they do produce something like letter X, such an X shape here. But at lower altitudes, they are roughly horizontal. Light polarization by dust. Just enough, 5 minutes will be enough for that. So, as I already said, non-spherical dust grains, aligned by magnetic field, they absorb the light whose E vector is parallel to the larger dimension of the grain. Then this means that they polarize starlight. And this map shows the polarization of stars at different positions in the Milky Way. So again, it's the same projection of the Milky Way. This is the mid-plane of the Milky Way, the galactic disk. This is galactic North Pole. This is galactic South Pole. This is here. It's anti-center. This is anti-center. This is the galactic center. So what we have, it's probably difficult for you to see, right? There are many, but look here. This black region, in fact, these are many dashes put together. So you can see clearly here that the polarization planes of stars, they have large-scale order. Here, when we look along the local arm, there is no this order. Not surprising, because we look along the magnetic field. And then these particles can be oriented anyway along the magnetic field when we look along. There is no polarization. When we look across magnetic field, all of them will be on average oriented similarly. There will be polarization. So there is no polarization when we look across magnetic field and stronger polarization when we look across it. But beautiful data. There are thousands of such galaxies, of such stars, but unfortunately the dust grain physics is so complicated and poorly known that it's practically impossible to interpret this data quantity. Fantastic, you see large scale order. Can we estimate magnetic field? No, we can't. Because we don't know exactly what is the angular velocity of rotation of these dust grains. What are their magnetic properties? What is their chemical composition? So the best we can do now with this is to calculate the ratio of the turbulent field to the large scale field from the scatter of the polarization index. And this is basically the only qualitative information about magnetic field that you can get from this very rich and beautiful data. Probably I should stop here for today. So tomorrow we can discuss what we have learned from using this from these observations. That's it for today. Thank you.
Thank you.
Question, please.
Everybody's tired. But anyway, I'm around here. I will be happy to answer any
So
questions.
Seemann, the discovery was done in 1903,
Or three,
right?
right?
Three, actually.
Three? Was it three? That's good.
Is that 3 years earlier?
I think it was 1903. And then 1908, this was observation of Hale.
Ah.
Guess what I'm... Oh. Ah, yeah, you can see it, right? Okay.
You can't hide anything.
I can, why? Of course I can.
You're trying, but you can't.
Why is that? That's not so good.
He's just showing his power.
So...
Historical references.
But it must be somewhere at the very top where, when it was discovered. Introduction.
Maybe.
Childhood and youth.
Nobel Prize already 1902.
1902, right? Ah, then it might be 18 something.
1902 received Nobel Prize.
Who got the references?
This, right? 1902 Nobel Prize.
Must have been before 97.
Because of his discovery, yes. Before 1997, yes.
Here, right?
Yes.
Lawrence heard about discovery in 1986. 1896. 1896.
disobeyed the direct orders of his supervisor. Smells.
He was fired, even.
Oh, okay.
Yes, let me highlight it.
So Zeman was fired.
No, no.
Oh.
Yeah, okay. He was fired for his efforts, yes.
Bad.
Not bad, right?
So one should disobey the direct orders of one's supervisor.
Maybe directors shouldn't behave like this, that one should disobey such a guy. Okay. Then that's time for coffee if there's no further question, yeah? Good.
Thank you.